In this video, we're going to talk about continuity. And basically what continuity says is that if you can draw a graph over its domain in an unbroken motion without lifting your pencil, then that graph would be considered continuous. So I have a picture here of a graph, and it is not continuous. We have a few discontinuities. So you'll notice we would have to lift our pencil if we were drawing at x equals 1. X equals 1, that could be called a jump discontinuity. All right, so that's a break in a graph or a discontinuity. Also, at x equals 2, because there's a hole in that graph, technically we would lift our pencil. Same with at x equals 4. So, at x equals 2 and x equals 4, we have what is called a removable discontinuity. All right, so these are breaks in the graphs. These represent discontinuities. You don't need to know the specific type of discontinuity. You just need to know that it's a break in the graph. And the reason we need to understand continuity is that once we start moving forward and we talk about rules for derivatives and integrals, being a continuous function is a requirement in many of our theorems. So continuity can also be sided, meaning from one side or the other. So as we look at this definition, we'll say let C, the number we're approaching, C is a real number on the interior or at an endpoint, so inside some interval or at the end of the interval. The function f is continuous at C, right? So the limit, if we look at the limit approaching that number, the function is continuous if it matches the function value. If I were to plug C into that function, and I would get an output value. All right? And then we can just also have right-hand continuous and left-hand continuous as well. But the main idea for continuity is when we look at the limit, if that limit value matches the function output value. And I've pulled a picture in here, so this just illustrates that sided continuity I was just mentioning. You can have continuity from the right, so approaching from the right. You can have continuity from the left, and then you can have two-sided continuity. And what we said for two-sided continuity is that the limit, as x approaches whatever that C value is, that limit needs to match the function value. And a function doesn't have to go to the left and right forever to be continuous. It can be continuous over its defined domain. So here we have a graph that we've looked at recently in a previous video. It's the top half of a circle, radius 2, and it is continuous over its domain. And the domain of y here is that my x values fall between -2 and 2. And there are no breaks anywhere on that graph when we would draw it. So even though this graph does not continue to the left and the right forever, it doesn't have a domain of all real numbers, it's continuous on its given domain. Let's look at a couple other examples of continuity or discontinuities. I've pulled in 4 graphs here, and only one of these graphs is continuous. So this first graph, part A, this graph is continuous. Now, graph B, you notice there's a hole or a circle in the graph. Graph B is discontinuous, but we could plug that hole up and make it continuous, right? We could extend the domain so that it would include f of 0 equaled 1. Right now, the domain for this function is all real numbers except x equals 0. And in this situation, we could plug that up. All right, our third example, C here, you'll notice when we look at this graph, we have a hole in the graph, but there's also a defined point at 0, 2. This is a removable discontinuity. All right, example D, we have a step function or maybe a piecewise graph. This represents a jump discontinuity. And if we move down here, we have two other pictures. E, we have a vertical asymptote on this rational function graph. So E is a infinite discontinuity. And F, it is discontinuous because we have a wild oscillation. So it is a oscillating discontinuity. So I hope that visually helps you understand what a discontinuity is.